Hello everyone, welcome to our first online class. Today we're going to be starting with section 3.4.4, which is on inverses. So I want to relate this and motivate this using some stuff that we've talked about before. Let's say that we have a linear system here. So I have the one x plus 2y is equal to 1, 4x plus y plus 2z is equal to 2, and y plus 3z is equal to 3. So we've seen before, this system is equivalent to the equation given by this matrix right here, times the vector x, y, z is equal to the vector 1, 2, 3. What's happening here is if you multiply this matrix here times this vector here, then you would get a 3 by 1 vector where the entries are just going to be x plus 2y, the first entry, 4x plus y plus 2z for the second, and y plus 3z for the third entry. And that's why these two, this linear system is equivalent to this matrix equation over here. So we're going to write this matrix equation as just ax is equal to b for short. So let's say that let's relate this to algebra first. So in algebra, just basic algebra with numbers and variables, we have ax is equal to b. This could be solved by dividing both sides of the equation by a, which for today I want to think of as multiplying by a inverse. Specifically, I want to multiply on the left because I'm not going to be making any assumptions about things being commutative, which with numbers, yes, of course they are, but in general, maybe not, especially with matrices. They will not be commutative with matrices. So anyway, as I have ax is equal to b, and I multiply both sides on the left by a inverse, right? And then if I do so, then of course on the left here, I could really think of this as using the associative property first. Excuse me. Associative property, and then combine the a inverse with the a, and then those go away, and I'm left with just x on the left side. And on the right side, I get a inverse b, which if we're in algebra, we would write as b over a, but really you want to think of this as just a inverse b. All right, so how do we do this with matrices? All right, so as a note, what we really want here is the existence of some matrix, which we'll call A inverse. A inverse is the matrix that we want to find, such that if AX is equal to B, then I can multiply both sides by A inverse and get that X is equal to A inverse times B. Right, so I want this A inverse A to go away. Maybe let's do a little bit nicer color. I want this A inverse A to go away and to be left with just X on the left side, and then A inverse B, which should be some vector on the right side. All right, so in other words, for this A inverse A to cancel, I really want to think of this as just in the algebra case, A inverse times A is equal to 1. So what is our 1 with matrices? Well, it's the identity matrix. So really I'm looking for, an A inverse such that A inverse times A is equal to the identity matrix for some value of n. All right, so A inverse exists in our case, and I'm just going to tell you what it is and tell you later how we can find it. But just know that in general, an A inverse does not necessarily have to exist. We'll see later that the existence of A inverse just amounts to basically whether or not our matrix is singular, or if it is row equivalent to the identity matrix. All right, so anyway, in our case, the identity matrix does exist, and this is what it is. Just this whole 3x3 matrix right here. Notice that all of the entries in here are being divided by a 23. So I can, just to make our lives easier with calculations, I can factor out this 1 over 23 from the entire matrix, and I could do my multiplication a little bit easier this way, so that, you know, my matrix now just has nice round whole numbers, and so when I multiply things, it won't be like as ugly. All right, cool. So here I'm just telling you that this is our A inverse. Let's check that it actually is our inverse matrix. So we'll take this A inverse, this thing that I claim to be the inverse of A, and I'll multiply by A. And what do I get? Well, all right, first row times first column, do this, I should get -1 times 1 plus 6 times 4 plus -4 times 0. That should give me -1 plus 24, and that is equal to 23. And over here, you see I had simplified this to just be a 1 because I still have this 1 over 23 pulled out on the outside. So this entry in our resulting matrix will just be equal to 1 because I factored that 1 over 23 out in the beginning. Great. All right, let's do first row, second column. That would be -1 times 2 plus 6 times 1 minus 4. And of course that comes out to be 0. And you can keep doing this for all of our entries. And just trust me that it works out. I checked it on my own. You should check it for yourself. Pause the video and check it for yourself if you would like to. This is equal to our 3x3 identity matrix. Great, so this is actually an inverse matrix. It should not be obvious to you that if I multiply A on the right by A inverse, then I also get the identity matrix, but in this case, it actually does turn out to hold. That doesn't always hold, but I will give you a criteria later in class for when you can assume that it's going to hold. All right, anyway, so let's relate this back to what we were trying to do. We were trying to solve this matrix equation, AX is equal to B. And so we found our A inverse. I just told you what it was. Now we can use it to say that our solution, our vector x, which is going to solve our matrix equation, is just going to be given by A inverse times B. So now that I have A inverse, I just multiply A inverse times B, and I should get my answer. So here I have, this is my A inverse, and this is my B. And if I multiply all these out, I get the following. So maybe let's just check that our second entry is correct. So we should get a 12 over 23 out. So if I do our second entry, I should get, that should correspond to row 2 times column 1, because this is the entry 2, 1 in our resulting matrix or vector. So I should get 12 plus -3 times 2, which is -6, plus 2 times 3, which is +6. So 12 minus 6 plus 6, that is equal to 12. Those 6's are going to cancel out. And then don't forget, I'm multiplying by this 1 over 23 on the outside. So I should divide my 12 by 23 for our final answer. Great. So anyway, our vector x is now given by this vector right here. So the variable x is equal to -1 over 23, y is equal to 12 over 23, and z is equal to 19 over 23. And that should solve our original linear system at the beginning. So x plus 2y is equal to 1, etc. I could just plug those variables, I could plug those answers of x, y, z into that equation, that system of equations. All right, cool. So, as a note, in the above, we only required that A inverse times A is equal to the identity matrix. So I'm thinking of this as being like a left inverse. We did not require that A times A inverse multiplying on the right is also equal to the identity matrix. So this right here, if I multiply on the left, we're going to call this a left inverse, and if I multiply on the right and get the identity matrix, that's called a right inverse. Right? I'll give you that definition in a second. But anyway, with square matrices, this will always happen anyway. But if your matrix is not a square matrix, so like if you have like a 2 by 3 matrix, then your left and right inverses are going to be different notions. In fact, you can only have at most one left or right inverse. Could also have neither. But anyway, so definition, matrix has a left or right inverse if, which we'll call A inverse, if A inverse times A multiplying on the left is equal to the identity matrix, that's for left inverse, and then right inverse is if A times A inverse multiplying on the right is equal to an m by m identity matrix. Note that this is an m by n matrix A, and therefore if I look at the sizes of A inverse and A, so A is going to be an m by n, right? So A inverse is actually going to be the reverse of that, which would be an n by m. So here again, if I have m by n for A, looking at right inverses, then A inverse would be an n by m as well, and therefore here the size would be m by m. So in particular, we're not even getting the same identity matrix, right? We're getting different size identity matrices. Okay. All right, cool. So I told you how to use inverse matrices. How do we find these? So we're going to use some material that we talked about in the previous section. So let's say that A is row equivalent to the n by n identity matrix. Using some terminology that we talked about before, this says that A is a non-singular matrix. So if A is a non-singular matrix, you could row reduce it to the identity matrix. These row reductions, these row operations, correspond to elementary matrices, which we'll call R1 through Rk, such that if I take the product of A and R1 through Rk, multiplying on the left, this should give me the n by n identity matrix. So anyway, this over here represents you do A and then you do row operation 1, row operation 2, ... up to row operation k. And eventually that should give us our identity matrix. So anyway, if I put parentheses around R1 through Rk, this product is being multiplied on the left times A to give me the identity matrix, and therefore we can think of this product of matrices as being A inverse. So A inverse is equal to the product of these row operation matrices, these elementary reduction matrices. So we can obtain this matrix by just doing those same row operations to the identity matrix. Right? So we can obtain this A inverse by doing those same row operations to the identity matrix. I don't actually have to find these matrices and multiply them all together. What you actually do is just think of this as just being the matrix that you obtain by doing those row operations to the identity matrix, and it's going to be a lot more time efficient. All right, so let's return to our example. Let me show you how with our matrix A to actually find A inverse. So what I do first is I find row operations taking A to the identity matrix. Then I do those same row operations and I take the identity matrix via those row operations to A inverse. Okay, so here are the row operations. Let's just kind of go through them one by one. So right here with A, I have a pivot in the first row and in the second row. So I'm going to use the 1 in the first row to zero out the 4 in the second row. So I'll just do -4 times row 1, add it to row 2, make that entry a 0. Now we see that our first column is all good. We have a 1 and all zeros below it, so that's perfect. All right, second row, we have a 1 in the bottom, a 2 in the top, and a -7 in our middle entry. So what I chose to do was I just added 7 times row 3, added it to row 2 and replace. And that'll zero out this entry right here. And then in the next step, I did the same thing with that 1 to zero out the 2 that was above it to make that a 0. So I did -2 row 3, added to row 1 and replace, etc. I also divided row 2 by 23, multiplied by 1 over 23. And then I am left with this matrix right here. I can get rid of the -6 and the 3 using this 1 in the middle here, get to this matrix, and then I can just swap this row and this row, rows 2 and 3, to get our 3 by 3 identity matrix. So these row operations right here take our matrix A to the identity matrix. So if I take those same exact row operations and do them to the 3 by 3 identity matrix, then that should take me to my A inverse. So this is how we find A inverse. Okay, let me get rid of some highlighter stuff. Great. Great. All right, so anyway, I take my 3 by 3 identity matrix and then I do that exact sequence of row operations. I do -4 row 1, add it to row 2, I get this matrix. I do this one, I get to this matrix. I'm just going to kind of go through it a little bit faster. I think that you really learn this by doing these examples for yourself, so I'm just kind of leaving this here for you to go through it on your own if you need to. Okay, so anyway, you do these row operations, and assuming that you do them correctly, which, let me just tell you, whenever I'm doing these myself, I have a very high likelihood of messing up one of the, I don't know, 20 different calculations that I do along the way, because there's a lot of things to keep in your head. It's really easy to mess something up along the way. That's completely fine. So what you need is a way to check that your answer is correct. So how do I check that an inverse is correct? Well, I actually did the check for us up above. This is how I always check that my answer is correct. So I found my A inverse, and I just multiply on the left by my matrix A, and I hope that I get the 3 by 3 identity matrix. If I don't get the identity matrix, then I realize that I messed up along the way, and I have to go through my work and make sure that and try to find my mistake, because if I'm not getting the identity matrix, then I did make a mistake. And so that's our check to find out whether or not we made a mistake. All right. So anyway, this is our inverse. That's how we find them. All right, cool. What's the usefulness of this? So let me remind you that our motivation was I have this matrix equation right here that I want to solve, and I could have just as easily solved this linear system by putting it into a matrix and row reducing that matrix. What I did instead was I took my matrix A, row reduced that to the identity matrix, and then took my identity matrix and row reduced that with the same row operations to A inverse, which feels like it might be more work. However, once we have our inverse, that's actually really useful to have. So anyway, this note is sort of explaining that. So to solve Ax is equal to B, like I was just saying, we could have just row reduced this matrix right here and gotten this matrix. That would have worked just fine. So here's the usefulness of having our inverse matrix already. So let's say that I wanted to solve this equation, which is Ax is equal to B, and also a different matrix equation, Ax is equal to C, with some different C, but the same matrix of coefficients A. So if I wanted to solve this, then I would put a different C in for this at the end here. Instead of B being 1, 2, 3, I could have C is equal to 4, 5, 6 or something. And to figure out what the solution to that is, I would have to just row reduce all over from scratch again. And if I had to do this 5 different times, I'd have to row reduce the same matrix 5 different times. And that would, quite frankly, be really annoying. So what you want to do instead is use the inverse matrix, because then you can just solve it immediately by doing matrix multiplication, because the answer to Ax is equal to C for any C is just going to be X is equal to A inverse times C. Doesn't matter what C is. You just always have A inverse times C is your answer. Once you have the inverse matrix, then this is just like really easy to repeatedly do this process. And we've already seen a couple of examples of this where this is useful. So I'll just let you know, like, and so there's this one type of problem that we've seen already where we are trying to find a matrix representation, and we want to write something as a linear combination of some vectors, except we want to write, say, like 3 output vectors as a linear combination of some vectors. That actually amounts to solving a couple of Ax is equal to B matrix equations, and so those can be solved just by finding the inverse matrix and saving ourselves a lot of work to not have to like row reduce a bunch of times. So anyway, I don't want to talk too much about that. If you're curious to see more about that, maybe like post in the comments or send me an email or something like that. I can maybe do something more with that. But anyway, so here's some facts about invertible matrices. So a matrix is invertible if and only if it is a non-singular matrix. So before we already talked about one of the directions of that. If a matrix is non-singular, then it is also invertible, because I just described to you how to find our inverse matrix. The other direction is pretty much the same. If it is invertible, then it also has to be non-singular. The reason being, any invertible matrix has to be row equivalent to the identity matrix, because the inverse matrix actually tells you what your row operations basically are. And that tells you that it is a non-singular matrix because it is row equivalent to the identity matrix. All right. I've kind of been brushing left and right inverses under the rug for a little bit. So here's a fact though. if a matrix has both a left and right inverse, then they are both equal. So if you have an inverse matrix A inverse, so if BA is equal to the identity matrix and AC is equal to the identity matrix, then in fact B has to be equal to C. That's basically what this is saying. In particular, this is telling you the following corollary. If A is an m by n matrix with m not equal to n, so in other words, it's not a square matrix, then A can have only a left or right inverse, or it could have neither, but it can't have both. So the reason being, if BA is equal to the n by n identity matrix, and AC is equal to the m by m identity matrix, is this right? Yeah, this is right. B, because A is an m by n, then B would have to be n by m, and then you get the n by n identity matrix. And then similar for A times C, this would be an m by m. Okay. Well, okay, so I'm sort of brushing some stuff under the rug here, but it should not be obvious that B and C cannot be equal to each other here. I'm not gonna go into this proof, but I just want you to know that for non-square matrices, you can only have a left or a right inverse, or neither. So if A is not a square matrix, then your left and right inverses cannot be equal to each other. You just can't have both of them. Okay. Let's get rid of that and move on. Okay, so here's an example. I would prefer you to use this as a time to do this example on your own. So here is a matrix that is 2 by 2, 1, 3, 7, 9. I want you to use the above strategy to find the inverse of this matrix and use it to solve the following two linear systems given below. So this one right here, should not erase. This one right here and this one right here. So these are the matrix, these have A as like the matrix of coefficients for them, and so these are both able to be put into matrix equations. So if you have a pad and paper at home, pause the video, try this example on your own, and then we'll go over it. All right, cool. So I'll assume that you've had time to try this on your own. So now I will just go through with the example, the solution. All right, so I'm going to do something a little bit different here. So I'm going to row reduce A and the identity matrix simultaneously to save time and space. So if you remember, what we were doing before was I take A, I row reduce it to the identity matrix, and then I do those same row operations, do them to the identity matrix, and I should get A inverse at the end. So instead of just writing the same row operations twice, I'm going to write them once and just put A and the identity matrix just side by side in like one really big matrix, and then row reduce that. All right, so on the left I have A, and my goal is to reduce this to the identity matrix. So first things first, I have a 1 in my 1, 1 entry and a 7 in the entry below it. I'm going to zero that 7 out by taking -7, row 2, add it to row 1. Should get a 0 there. That should do this to the identity matrix. I should just get a -7 there. All right. Next thing's next. I will get rid of this negative 12 by multiplying the entire row 2 by negative 1 over 12. That'll have this effect on this row. Then I zero this 3 out above, and I should get a 0 there, and I should get negative 9 over 12 there, and a positive 3 over 12, which reduces to 1 over 4. And so on the left, I have my 2 by 2 identity matrix, and on the right, because I have the identity matrix on the left, I should have our inverse matrix on the right. So this is our A inverse. So each of these I could think of as having a factor of 1/12. This 1/4, I'm just going to think of it as 3/12. In a lot of examples, I would actually prefer to leave this as 3/12, just so I can factor that 12 out at the end a little bit easier, and I'll do that in some of the practice exercise at the end. So anyway, this is our inverse matrix. And to check that I did it right, what I could do is just multiply our matrix A times our inverse matrix right here, and hope to get the identity matrix out. And it's like I didn't actually do that in the notes. Maybe let's just take some space over here and just do it real quick. So let's do 1 over 12, negative 9, 3, 7, negative 1. Times this matrix here. So our first entry should be negative 9 plus 21. That's equal to positive 12, which is going to become a 1 because of this right here. Our next entry will be negative 27 plus 27, right? Negative 9 times 3 plus 3 times 9. That'll be 0. Next one, I'll have a 7 plus negative 1 times 7. That'll be 0. And then I have 21 minus 9. So that's also going to be equal to 12. And so this is equal to our identity matrix. So perfect. Okay, let's get rid of that so it's not so clunky. All right, cool. So let's use that to finish our exercise. So I can take my A inverse and multiply it by my B matrix to get our solutions. So I would take my A inverse, multiply it by 6, 7, and I should get this matrix out. I won't go through that. And then same thing for multiplying it by the vector 2, 4. That's going to solve this one and this one. All right, cool. So 2 by 2 matrices are pretty easy. So here's a theorem that'll just give you the formula for your inverse of a 2 by 2 matrix. So 2 by 2 matrices are almost always invertible. If I have my matrix is given by A, B, C, D, then so as long as AD minus BC is not equal to 0, then A inverse is going to exist, and this is going to be our formula for it. So our formula is just we take the diagonal entries and just switch their spots, and our off diagonal entries, I keep them in the same place and I make them negative. And then on the outside, I just multiply by 1 over AD minus BC, which we're assuming to not be equal to 0 in this case. Okay. The proof of this is really just a calculation that you can just row reduce A, B, C, D to the identity matrix and then see what your inverse matrix has to be, and it turns out to be this. All right, so I'll leave you with a practice exercise that you can do on your own. I will leave these notes on Canvas, but just to keep the video a little bit on the shorter side, I will maybe not go through the practice exercise in full detail. I'll let you just do this for yourself and check with the notes to see that it's correct. I want you to find the inverse of this 3 by 3 matrix A and use it to solve the matrix equation AX is equal to B, where B is equal to 1, 2, 3. So yeah, so the solution is posted online. I would prefer you to do this on your own to get some practice with the material. If you would like me to, in the future, for future online lessons videos, to have these practice exercises at the end and me actually going through the solution after maybe say a 10-second pause so that you can pause the video and try it for yourself and do the solution. If you want me to do that, I'd be happy to. I'm just opting not to now just to save time. I am also happy to just include a bunch of these practice exercises at the end to sort of just supplement the practice exercises on the workbooks online homework. I'm happy to include more of those and just write up my own solutions to those. So whatever you all want, I'm happy to accommodate just to make this a better learning experience for all of you. So anyway, we'll end it there. Thank you all for listening.